The cosmos is amazing. To put it another way, only 4% of it is made up of the particles that make up our bodies, the visible universe, and all of its regular matter. The majority of the universe's mass, which accounts for 70% of it, was only identified in 1998. Even though no one has the foggiest idea of what it is, we refer to it as dark energy. Every galaxy has a supermassive black hole in its center. Frequently, active galaxies emit 100 times as much light as a typical galaxy. It became abundantly evident that the light originates from a core region smaller than the solar system rather than from stars with the discovery of quasars in 1963. Only matter heated to incandescence as it pours down onto a massive black hole up to 50 billion times the mass of the Sun is a source of energy that is possible. Supermassive black holes are not unusual, according to research conducted in the 1990s by NASA's Hubble Space Telescope, despite the fact that active galaxies make up just approximately 1% of all galaxies. There is one in almost every galaxy, including the Milky Way, but due to a lack of food, the most have turned off. Supermassive black holes, what are they doing in the centers of galaxies? Were these the initial galaxies that coalesced around? Or did they originate from young galaxies? These still rank among the most important unanswered issues in astrophysics. Everywhere in the universe is the same temperature. The universe contained the heat of the Big Bang fireball. Since it had nowhere else to go, it is still present today. Its temperature, which is 2.725 degrees Celsius above absolute zero, minus 270 degrees Celsius, the lowest temperature imaginable, remains unusually consistent throughout. However, if we think of cosmic expansion as happening backwards, like a movie that has been reversed, we discover that regions of the universe that are on different sides of the sky right now were not in contact when the fireball of radiation broke loose from matter. In other words, from the beginning of the universe, there hasn't been enough time for heat to move between them and the temperature to equalize. Astronomers correct this by arguing that the universe was initially considerably smaller than anticipated, which allowed heat to spread easily. The universe had to undergo an initial burst of extremely rapid expansion, known as inflation, in order to reach its current size from this lesser size. The universe is mostly invisible, 95%. The majority of active scientists are still unaware of this astonishing discovery, which states that everything science has been researching for the past 350 years is really a small contaminant of the universe. Atoms, which make up you, me, the stars, and galaxies, make up just 4.9% of the mass energy of the universe, and, of that, only half has been spotted with telescopes. Dark matter, which makes up approximately 26.8% of cosmic mass energy, may be seen because it pulls on the visible matter with its gravity. Black holes created during the Big Bang and previously undiscovered subatomic particles are candidates for what makes up dark matter. Dark energy makes up 68.3% of the universe's mass energy, yet it also exists alongside dark matter. It is completely engulfing all of space, invisible, and speeding up cosmic expansion. The energy density of our best hypothesis, quantum theory, is overestimated by a factor of 1 followed by 120 zeros. The creation of the cosmos. The universe has not always existed. It was created. The Big Bang, a gigantic conflagration that brought all matter, energy, space, and time into existence 13.82 billion years ago. The explosion started to grow, and finally, the galaxies, large islands of stars, of which our Milky Way is one of an estimated 2 trillion, formed out of the cooling debris. This is the Big Bang Theory in a nutshell. Any way you look at it, the notion that the universe appeared from nothing and that there once was a day without a yesterday is completely illogical. But the evidence points to that. The question of what occurred before to the Big Bang immediately emerges. Most scientists had to be coerced into accepting the theory of the Big Bang because they were unwilling to tackle this unpleasant subject. Gravity is a force that repels most matter in the cosmos. Like cosmic shrapnel after the Big Bang, the individual galaxies that make up the expanding cosmos are tearing themselves apart. The only force at play should be gravity, which slows the galaxies down by functioning as an elastic web that connects them. But contrary to all expectations, astronomers found in 1998 that the universe's expansion is really speeding up. As a potential explanation, they suggested the existence of dark energy, an unobservable substance that fills space and has an attracting gravity. The universe is expanding more quickly as a result of the dark energy's repellent gravity. Dark energy makes up almost 2/3 of the universe's total mass and energy. Therefore, according to school science, the idea that gravity has no utility is outdated. A large portion of the universe is affected by it. Only 1/3 of the expected neutrinos are being produced by the sun. Hold up your thumb. Every second, 100 billion neutrinos pass through your fingernail. 8.5 minutes ago, they were in the sun's core. Solar neutrinos are a consequence of nuclear processes that create sunshine. When Ray Davis set out to find them with 100,000 gallons of cleaning solution down a mine in South Dakota, he expected to confirm the general understanding of the sun. Instead, he only found about 1/3 of the predicted neutrinos. This finding earned him the Nobel Prize and was later verified by other studies. Neutrinos are spectral subatomic particles that are like an animal that is simultaneously a cow, a pig, and a chicken. They exist in an odd quantum superposition. Studies that are sensitive to only one kind only detect 1/3 of the anticipated amount because as they go away from the sun, they switch between being an electron neutrino, a muon neutrino, and a tau neutrino. In comparison to other planetary systems, scientists are hesitant to identify any special characteristics of our planetary system. Normal is more likely than special, which is unlikely. The discovery of planets orbiting other stars, of which more than 3,500 have been confirmed as of the most recent count, has presented a challenge to astronomers. None are as good as ours. There are planetary systems out there that are so tiny that Mercury, the innermost planet in our solar system, orbits the sun more closely than all of the planets do. There must have been internal movement of planets with the mass of Jupiter. There are planets that have incredibly elliptical orbits, similar to comets. Furthermore, some planets orbit their stars in the wrong direction. Given that it defies the commonly accepted belief that planets form when gas and dust swirl in the same direction around a young solar system, the latter discovery is particularly difficult to explain. Nobody knows for sure yet if our solar system's oddities are related to the fact that humans have developed the ability to see them. First detected gravitational waves were produced by an unexpected binary black hole system. On September 14, 2015, the first gravitational wave detection on Earth took place. Einstein predicted in 1916 that these swells in spacetime would occur as a result of the merger of two black holes in a distant galaxy. In other words, the amount of power generated was 50 times greater than the combined power of all the stars in the universe. However, this was not the only incredible aspect of the event. Between 30 and 100 solar masses were the masses of each black hole. Since a black hole is what is left over when a star explodes as a supernova, the progenitor stars must have weighed at least 300 solar masses. Such stars are incredibly rare today. The two black holes, however, could have been the first generation of huge stars or perhaps primordial black holes that formed after the Big Bang itself. We appear to be alone. There are roughly 100 sextillion stars in the universe, and perhaps more planets than stars. But in all of this space, we only know of one place where life exists, the planet Earth. Despite looking for intelligent signals, no proof of intelligent extraterrestrial life has been found. In fact, There is a strong argument to be made that if such life exists somewhere else, we should not only be able to detect it, but also already have it. Enrico Fermi, a famous physicist, famously asked, "Where are they?" According to some astronomers, the only explanation is that humans are the first creatures that have ever existed. Lack of evidence, however, does not establish absence. Since it took 3 billion years for humanity to evolve from single cells to complex life, this step is challenging. Given the rarity and limited longevity of sophisticated civilizations like our own, we may have missed any such civilizations by millions or even billions of years. The alternative explanation is that the closest one might simply be too far away for us to detect. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.